Good morning. Today is April 7th, 2018, and this is the John Chappell Natural Philosophy Society Saturday Science Chat. I am your host, Franklin Hu, and this is sponsored by the Natural Philosophy Society. Please visit our website at www.naturalphilosophy.org, and you can become a member, and that'll get you on our email list so you can get notifications of conferences like this. And we also have forums which you can discuss things at forums.naturalphilosophy.org. And we also have a wiki where we have a lot of information on some of the theories that the scientists that belong with our organization work on. And we're also on Facebook. Give us a like. And we do have an upcoming conference on June 27th through the 30th, 2018 at the campus of the University of Connecticut. And we did just get an update about accommodations for the Critical Thinkers Conference. The title is Back to Our Philosophical Roots. So there's going to be a special economy dorm at the conference center. So that is a shared accommodation with 3 people to a room. And apparently the cost is per person at $69 a night. So I guess you need to pick your roommates. But that is now currently available. If you're thinking about going to the conference, it's coming right up. So this is a possible alternative for you to stay at the conference. I did investigate some other hotel rooms which may have been available. And you can get some, but they're kind of far away. They're about 20 minutes away. But you can get them also as little as $69 a night if you want to do something like that. Okay, so let's get going here. Let's see here. Who do we have here today? So you guys can hear me? Someone give me a shout out because I haven't heard anything from anybody today. Harry, can you hear me? Okay, great. Thank you. I just wanted to make sure I wasn't talking to myself. So today is a completely open forum. So I wanted to ask if someone has a topic they would like to float. Otherwise, my plan is to go down the line of atomic data that we've been looking at. So has anything been on people's minds this week?
I have put something in the chat box.
All right, Hans, what have you got in the chat box? Let's see.
It's
here.
An article about how mass is generated, and it can only be generated very temporarily, so it must continuously be regenerated. And the generated mass dilutes into the expansion of the universe. So mass pumps a little bit volume locally into the universe, and that volume quickly spreads over the whole of the universe, so the whole of the universe expands, but the deformation that's created goes away, fades away in that way. So a process that wants to create mass must do this in a recurrent way, such that at the same location on a regular basis, new mass is created.
All right, so let's see here. Now I clicked on your link, but I think you put a semicolon at the end of it, so I had to remove that. But let's see here. Let's go and take a look at that. Okay, so, but this is a new paper you have then. Got your name on it.
Yeah, I write regularly new papers about the same thing, about the Hilbert book model, and I treat aspects of that theory and deepen them out. And one of the things that I didn't bring in words too specific is the fact that spherical pulse responses are capable of infusing volume into the field that they affect. So they create volume into the field, and that volume deforms the field. And deformation has something to do with mass, at least in the field that represents our living space.
All right, well, let's go over your paper here. It's not too long. It looks like it's only
three pages.
Three short pages. I think we can probably cover that. So not having read this in here, so you explained your abstract here.
Yeah, and the paper treats more things. It also treats, for example, it looks at the quantum wavelength of electrons, and from that same formula, it derives at what rate electrons are regenerated. So the electron must be regenerated, its mass must be regenerated, and that goes with a certain rate. And that rate is the frequency of the annihilation photon that is produced when the electron annihilates. And that's frequency is 10 to the 20th, about that factor. It's at the end of the paper. This frequency is listed.
The lists a specific frequency, 10 to the 20th, which is an extremely high frequency, mind you.
Yeah, it is.
But let's see here. So you have an origin of mass.
Yes.
So you're saying you have this thing here. It says otherwise temporal local deformations would not perceive as attractive. What does that mean?
Local deformations are attractive.
Sorry, what does that mean? Why would they be? I mean,
that's the fact that goes together. They produce a local deformation, and they produce at the same time an expansion of the universe. And the effect is that if they produce a swarm of these local expansions, the local deformations, then this swarm grows faster than the universe grows. So it looks as if these things are approaching each other.
So, I mean, are you trying to explain gravity here? Is that what you're trying to do?
Yeah, exactly.
But you're talking about local deformations. Now, are you talking about like the moon being a local deformation?
The moon is certainly a local deformation of our living space. Any massive object is a local deformation of our living space. But already the elementary particles do this.
So somehow, see, in the first, so you say the universe must expand. Now, so how does that cause local deformations to be perceived as attractive?
The same mechanism that infuses a volume into locally into the universe is that volume stays there. So the whole universe, the volume of the whole universe increases as soon as the infusion takes place. But the infusion itself, the local increase of the volume, is not staying there. It spreads over the whole of the universe, so it spreads out, and the deformation goes quickly away. So if you want to keep a deformation, you must recurrently regenerate that deformation. That's what the process does, that creates and recreates the electrons in a continuous way.
So your second paragraph says stochastic processes generate the pulses. So why don't you explain what you mean by stochastic, first of all, since some people might not know exactly what that means.
It is, as far as I can see, It is a combination of a Poisson process. You know what a Poisson process is? There's a stochastic process.
See, that's what I'm trying to get you to explain. I'm trying to get you to explain this in a way that people can understand it in words they might recognize.
Well, if a Poisson process is producing a lot of output, then it produces a normal distribution. So a Poisson process is a sparse form of the process that creates a normal distribution.
So is that what you mean by? I mean, why don't you just say a statistical process? Would that be the same thing?
It is a very specific statistical process. It is a process that of which the variance depends on the number of generated output locations, for example. So the variance of those locations is well defined by the definition of the Poisson process. But I was not completely finishing what the definition of the stochastic process is that takes place here. Then it is a combination of a Poisson process and a binomial process. And the binomial process is implemented by a point spread function, a spatial point spread function, that in fact spreads the output of the Poisson process over a certain area according to the point spread function. And the point spread function is something that you might know from imaging. Imaging is also using the notion of point spread function, where you like to have a single point as the image, but most imaging devices don't make the point, but make a point spread function, a blurred point image. So the process make a kind of blurred point-like Poisson process.
Okay, I'm still not sure I understand what you mean, but the second sentence is that they create mass out of nothing, which I think is a remarkable statement. So you're having a pulse, right? That happens by some statistical process, creating a regular distribution, and somehow they create mass out of nothing.
Yeah, that it is not directly clear why the stochastical process is doing the thing that it does, but in fact, what occurs is that in the model, the Hilbert book model I'm talking about always, the separable Hilbert space. There's a set of separable Hilbert spaces, and an elementary particle is represented by a single separable Hilbert space. All these separable Hilbert spaces are embedded into a non-separable Hilbert space, and the non-separable Hilbert space is a storage place for continuums. And one of these continuums is our living space.
Well, let's go back and look at, so now your Hilbert book model, now was that an analogy to like a book, and that each moment in time is represented by a page in that book?
Yeah, exactly.
Okay, so that is the Hilbert book model, right?
Yeah.
So as time goes by, it's just like reading a book, where so a particle appears like in the middle of the book. Then as you flip through the pages, you could see it, move like down or do something.
Yeah, so, that's the general idea. That's why I called it the Hilbert book model. In fact, at every next instant, each separable Hilbert space that represents an elementary particle gets a new location. So in its own Hilbert space, in the eigenspace of one of the operators there, the elementary particle is hopping around. And make a hopping path. And after a while, that hopping path is creating a complete hop landing swarm. And that hop landing swarm is what at the end forms what we know as the wave function. The wave function is a descriptor of this of the location density distribution of this swarm.
Okay, so we don't. So it's kind of postulated that these things create mass out of nothing.
Yeah,
So,
no, yeah, it is to make it to put it there
that's
and
okay. I guess
to make it attractive and draw attention to the people. Nobody believes mass can be created out of nothing, and in fact, it is not nothing, but it is a mathematical model that embeds a separable Hilbert space into a non-separable Hilbert space, and that's in fact what's behind the continuous recreation of mass.
All right. Well, I'm going to tell you right now that I find that kind of a hard nut to swallow.
Yeah,
Because I'm one of these people who believes
everybody does. I put these things sometimes at Quora and at ResearchGate, and some people react very furiously onto my claims. But I can in fact give it a good mathematical support.
I mean, basically, you're saying 0 equals 1 when you say you can create mass out of nothing mathematically. So
yeah, and it goes away to nothing as also.
And 1 equals 0. So that those are two equations that basically violate everything we know about mathematics, though. Would you agree?
Yeah. As soon as you can accept that something can put volume in our living space, increase the volume locally, and that this volume spreads out all over the universe so that the universe expands, that means that this deformation that represented some mass is also fading away quickly. So it is created and then it goes away, but it dilutes into the expansion of the universe. The universe expands, and that's due to the fact that all these elementary particles are regenerated.
Well, are you saying like the particles of, say, the Earth are being regenerated?
Yes, but all elementary particles are regenerated. And the Earth is completely constructed out of elementary particles.
So all the particles that make up me are constantly being replaced.
Yes, that's the case.
Okay. So there's mass being created out of nothing, and then mass going away into nothing.
Yes, that's the
fact.
And it must be done. And the conservation of mass means then that the rate of creation of mass must be constant all over the universe. That's the conservation of mass.
Okay, we get that, but you're also saying that there must be an increasing volume of the universe. Why would there be an increasing volume if the amount of mass being created equals the amount deleted?
That the field, that in fact, a field can be represented by a function. And what you do is if you insert a volume in a multi-dimensional function, then you insert a bit of space between the target of the function and the parameter space of the function. At the start, when nothing is done, then the function equals its parameter space. But if you are starting infusing volume into that function, into that field, then there is a difference between the target value of the function and the parameter space of the function. That's what's happening. And if you do it locally, this field has the property that this inserted volume is spreading all over the field. So the whole of the field is expanding. It's like a balloon that at the beginning of its existence is flat, and after a while it's pumped more and more with more and more volume. So it's
yeah. So you see on your second paragraph here, you're saying only mass density decreases.
Yes.
So like you're saying, like an inflating balloon. So am I expanding as I'm sitting here? Is that?
Yeah. The volume.
I'm blowing up like a balloon, but I just don't notice.
No, but that's well accepted theory. The physics of this day accept that the whole universe is expanding and with fast rate.
Well, I don't think that's quite as fast as what. I mean, there are some other theories which say that the force of gravity is actually due to the surface of the Earth rapidly expanding at 9.8 meters per second acceleration. But you're not suggesting that, are you?
If you take conventional physics, they accept that via the Hubble theory, that universe is expanding. With some say that it is with a constant rate, and some say that is expanding in an accelerating way, so that it grows even faster. That these stochastic, it would mean that these stochastic processes are becoming more active.
Right. So you think that the mainstream says or the universe is expanding at a rate X, and so you're just explaining why it's expanding at that particular rate.
Yeah, you
nothing dramatic, not as dramatic as like the exploding Earth people.
Yeah. But if you want to explain gravity, then you need both these effects, and there is one mechanism that does it. That are these spherical pulse responses. They do insert volume locally, and this volume then spreads all over the field. So they do deform, and they do expand the field. It's one mechanism that does it all.
Okay, so I'm looking at your second thing here. You're saying the actuator of the spherical pulse must be isotropic.
Yeah.
What happens if it's not?
You need, and then I think nothing happens. There is no expansion. There is no volume inserted if the actuator is not isotropic. That's maybe the reason that, for example, quarks cannot direct make themselves visible. They first need to collect into mesons and baryons in order to become colorless, and then and colorless means isotropic, and then they can together make a punch into the field and make a spherical pulse response and pump volume into the field, and the field then reacts in a way that keeps these things together.
So maybe you might want to explain what you mean by isotropic.
That
just means that it's consistent.
In all directions, the same.
So that would kind of be the definition of a spherical pulse, right? All spherical pulses.
Yeah, that's the pulse response is spherical, and isotropic is in fact the pulse. The pulse response is spherical because it has shape, but the pulse itself is difficult to say that a point is isotropic of is spherical. A point cannot be spherical, I think, to my opinion.
A point cannot be spherical?
Spherical is something like a sphere. And a sphere cannot be a point.
Non-isotropic would be like if it sent out pulses in two directions, like when you have annihilation, you get two gamma rays going in the opposite direction. That would be non-isotropic, right?
Yeah. But already all quarks have color, and the color means that there is a direction that differs from the behavior in other directions. the color charge that they have is an indication of anisotropy.
So you're saying elementary particles. So you're talking about things like protons, electrons.
No, protons are not elementary. They are composed, but electrons are, neutrinos are, positrons and electrons are, and I think there are also bosons. I'm now talking about the fermions. The fermions is a very small set, at least the smallest versions. There are also muons and all kinds of these things that higher generations. But the stuff we are made of, that are only about 6 fermions that create nearly all stuff in the universe.
So does your theory explain, why don't we have more elementary particles? Is there some limitation? I mean, why couldn't there be like 23 elementary particles versus 6?
One of the reasons is that the quaternionic number systems exist in a limited set of versions. And these versions distinguish in the way they can be sequenced by coordinate systems. So you can use a number system and fill some space covered with that number system, and have a coordinate system, a Cartesian coordinate system, and a polar coordinate system in it. And the way that these spaces can be sequenced by the coordinate system distinguish between the different versions of the quaternionic number system. And there are only a few choices. And if you put them in a row, then you come to the conclusion that's the reason why we have the electric charges of the elementary particles and why there are color charges. It's not too difficult to understand. It's all part of the Hubble book model.
All right, so now we're in your paragraph 4 here, generation rate.
No, that's too short. But there is another paper, and that's called Structure in Physical Reality, and that's also in the same library, the extra library. And I'll put it in the chat box, the reference to that article. But that also explains why the different charges are there, why we have spin, and in fact, it is a somewhat larger story than this 3-page paper. It's a 13-page paper, and it contains most of the highlights of the Hubble book model. And the Hubble book model is itself is treated in a Wikiversity project. I put all my knowledge in a Wikiversity project.
All right. Well, I'm going on your paper here. So you have your generation rate here. So we've got some math. So here you're equating 2 equations. You're equating E equals MC squared and E equals HV. And then you're just equating MC squared and HV.
Yeah, that's
rearranging here.
I think that there are 2 very well-known formulas. One is Einstein's E is MC squared, and the other is Einstein-Planck relation. So the Einstein comes here back also, and that's what happens in a photon. In a photon, the energy equals the Planck's constant times the frequency.
Yeah, well, you can do these things, but I could kind of see, and people do these things, but the question is whether it's legal to actually make that equality. Now, maybe it is, maybe it's okay.
They are
results. I could say fruit
measurements.
I could say fruit equals apple, and I could say fruit equals orange, and then I could say apple equals orange.
Yeah, but these are not just theoretical things. The Planck-Einstein relation was measured very precisely, and also E sub c squared is measured very precisely to 15 decimals, I think. These are well established. They are not theoretical formulas. They are postulated and then checked.
They are certainly well empirically derived formulas, but one of them relates the quantity of energy contained in matter, while the other one relates to quantity of energy contained in a certain photon. So photons and matter would seem to be completely different.
Yeah, well, these things...
Whether you can equate those things together, I think it's kind of questionable.
These things come together if an electron is annihilating into photons. When a positron and an electron annihilate, per annihilation or per creation, then you get a conversion from electrons or photons, electrons and positrons in photons, or vice versa. And these processes take place very regularly, and they are quite commonplace in experimental physics and particle physics.
Well, that may be true. So you add all these things up, so you get a V here. Now that's very confusing because that means
no, that's the frequency. Sorry,
frequency.
It's frequency. I use V because
it's not velocity.
No, it's the nu, the Greek character nu.
Okay, so that's frequency, which is 1.2 times 10 to the 20th, which is really fast.
Yeah.
And the period, which is wavelength, 2.4 times 10 to the minus 12, which is really short.
That's the quantum wavelength. That's also a measured thing. The quantum wavelength is well established, and I think in the beginning of the 20th century, it was already measured and established that it was about the size of that wavelength.
Now you're saying here, I think your conclusion here in bold is that the clock frequency at which that this V or frequency may be the clock frequency at which the universe steps.
Yeah, that's because I think the electron is the most simple elementary particle. It has already all the properties that are necessary to make symmetry breaking. It has exactly the reverse symmetry of the background. So it breaks the background in a completely isotropic way. And so the electron doesn't have to do anything else than just the quaternion that represents the electron, the landing, has nothing to do than to land, and then it already happens, and there is no extra things are necessary to generate the pulse, the isotropic pulse. And with quarks, you need some extra measures to generate a group that is colorless, so that it becomes completely isotropic. And that is more work. But the electron is quite simple. So
well, in relationship to your book model, are you saying that like the rate at which each page turns corresponds to this clock frequency?
That's my idea. That's
okay. That's easy to understand. That if you have the Hilbert book, and the book is being flipped at a certain frequency, and that frequency is like 10 to the 20th pages per second.
It can be faster, but it must be at least as fast as this one.
Now I've heard this 10 to the 20th thing in relationship to the clock frequency of the universe. I mean, I have a paper that attempts to explain what time is, and coincidentally, the calculated frequency that I come up with for highest speed that anything can occur is, in fact, the same 10 to the 20th magnitude. So I thought that was just kind of curious that that both of our theories would kind of come up with that same number.
Yeah, there must be more reasons that say
the number may be related to like what you say here, which is that it's a relationship between the MC squared and the HV formulas. That number can be fairly easily pulled out. That you're not doing anything terribly fancy here to pull out this frequency and this wavelength and this energy.
Yeah, you can find these figures in any physics books. They are quite common. They are exist already for slightly less than a century.
All right. Well, I still find it difficult to believe that you can generate mass from nothing, but this is your postulate, so I'll have to say that that's what you're trying to explain. So, okay, so we've gone over your paper, so I'm going to open up the floor to questions from everyone else. So please, if you have a question for Hans, if you have any doubts, any questions, any suggestions, maybe Bob, you've got a comment. It looks like we have Jay Maxwell here.
So
that Maxwell, the Maxwell equations?
He's at least family.
Yeah, he's at least family. Mitch, are you trying to say something?
Yeah, I guess I kind of have a thought about the creating mass from nothing. It really, I don't think it really is in line with this paper, but when people tell me or when I hear that mass can be created from nothing, I'm a big fan of Glenn Borchardz's theories, and I kind of agree with him where he believes that mass is not really created from nothing. It seems like that because of the particles, like the ether particles or the atoms of the atoms, come together and form because they're too small to be detected, and they form bodies just like our atoms form. Eventually, they'll form a solar system or form a whole galaxy. Well, the same thing is happening in a microscopic levels too, but we just can't detect those very minute particles that are coming together and forming the atoms and the elementary particles.
Well, mainstream does have a very clear example of forming matter out of nothing. So you take two gamma rays and, actually any gamma ray of sufficient energy, you shoot that around a heavy nucleus, and then you will see something called pair production, whereas out of nowhere, a positron and electron appear into space. And so this is
that's not creating something out of nothing. That's creating something out of some auxiliary something.
Yes, that's auxiliary something. In this case, gamma rays.
So I think this whole statement of creating mass out of nothing is somewhat misleading.
I suppose it is. I guess mass out of non-mass would be more accurate.
Well, I'm not really sure
mass to pop out of space.
I'm not really sure what Hans means when he says out of nothing.
Now,
he actually is saying that.
Pair production can create mass out of photons, out of energy. And what I meant to say is it's indeed nothing. There is no energy involved. There is no, something new is created, and a volume of the universe, that's mass, and that mass can be converted into energy, but that comes from a completely mathematical source, which is the embedding of a separable hyperspace into a non-separable hyperspace. So there was content in some part of the model, and it is transferred from the discrete part of the model to the continuum part of the model.
But what you mean is you don't say that mass is created out of nothing. You're sort of saying, in my opinion, that it's created out of mathematics.
Yes. Yes, but that nobody. If I say that kind of things, then nobody would agree in any kind of way. But if you study what the embedding process does, then you come to the conclusion that something like this must happen. And there is a term called dynamic chiral symmetry breaking that's used in quantum dynamics and electroquantum dynamics and chroma quantum dynamics. That is also creating mass out of nothing. These people that speak about this kind of breaking say that it is creating mass out of nothing. And in fact, it is a similar process.
Well, I still have a big problem with mass out of nothing myself.
Yeah.
Kind of a positivist, But I mean, you yourself admit that, it would be somewhat accurate to say you're making matter out of math. I make
math out of math. It is another kind. I make one kind of math into another kind of math. I make continuous math out of discrete math. That's what's happening.
Yeah. Well, and that would be
you have
in
different
contrast
views
to,
on this.
Yeah, everyone has different views on this. As a physicalist,
well, I put Hawking's statement in the chat box if anybody wants to look at that. We had an argument about that about a week ago. There was a discussion about that on one of the astronomy sites, and it sort of boils down to what you mean by what is nothing.
Well, we've had lots of discussions about what is nothing. You'd think it wouldn't be that much to discuss, but a lot of people have a great difficulty with the seemingly intuitive idea that nothing is a place of just spatial dimensions that doesn't contain any physical particles. I mean, I don't know. That's kind of how I argue. But there'll be dozens of people arguing against that particular embodiment of space. So, let's see here. Do it as you will. I mean, I prefer to think that as a physicalist, that mass can actually never be created and never be destroyed. That is in fact completely conserved along with energy, but you have to explain these things like pair production and annihilation, and explain that those are not actually instances of matter being destroyed or created.
I would think that you have to justify your assumption as a physicalist. You're making an assumption, and you're just saying, because I made that assumption, this is what I believe.
Yes, well, that's an assumption which is based in our observations of the world. So if I have this particle here, I have never in my common experience seen this thing just like disappear. Okay. If you no longer see it, it's because I threw it away back there. So our common experience tells us, as a physicalist, that we shouldn't expect that things like this will just disappear into energy. So how can this be turned into something which is energy, which is kind of like motion, there's matter in motion. So that's energy. How can that be turned into this?
Yeah, but
we just don't see that in our common experience. So I would say that the weight of our common experience tells us that the physicalist hypothesis is the one that we know about. That there's no instance where I can have some macroscopic object just magically appear, not unless I'm a magician. Right?
Yeah, but problem is the mass is not well defined as a property. The property mass means that something is capable of deforming the continuum or the field in which it is living, in which it is embedded. If it deforms that field, then it owns some mass. And the degree of deformation is the amount of mass that's involved. So if deformation means that some volume has been added to this field, then you can comprehend the whole thing. And mass is not some property that is guarded, that is conserved. The volume can spread out, and it does, because the whole of the universe is expanding by this spreading of the volume. So if you
I don't see the volume of this thing increasing, Steve. So.
No, you never see it. You're part of that universe, and you are expanding with that universe. So you're completely fooled by that universe, by the fact that the universe is expanding.
Or this particle is just not expanding is the other alternative, right?
Yeah, that's what you.
Neither am I.
For me, you can believe anything you want.
But I'm saying, Harry's asking,
he does, Hans. He does believe anything he wants.
I mean, anyone believes whatever they want. I mean, it's just a matter of plausibility.
Well, you do it more than anybody else.
Well, I'm just saying that my beliefs are based on things that we can observe physically in the world around us, not mathematically, not in obscure experiments, but in fact in the things that we can hold in our hand microscopically. The behavior of matter is what we can rely upon, rather than giving it some other magical properties.
Yeah, you didn't meet enough magicians. Otherwise,
they can pull rabbits out of hats, right? How does that happen?
All these kind of things, yes.
Well, you kind of blew off the comment that I made about Stephen Hawking's statement. And Hawking made this statement that he's trying to explain away the fact that how did the Big Bang occur, because that requires that something come out of nothing. And he's sort of trying to explain that. So what's your thesis about that? I mean, if the universe had an origin, then it must have come out of nothing, right?
Are you asking me or Hans?
Well, you as a physicalist, you're sort of,
well, as a physicalist,
particular physicalist position on this.
My position on this is that as a physicalist, I do not like anything where matter comes out of nothing. So I would say that I have doubts about the whole Big Bang even happening because of that. As a physicalist, I would say I am more inclined to believe that the universe has always been here, since I believe mass is conserved. So it can neither be created nor destroyed. So what we see must have been there all the time. Therefore, there could be no beginning. There is no end, and that the current evidence that we have for the Big Bang, which is just this redshift thing, can be explained as just a distance-related effect, where the wavelength just simply gets redshifted due to the fact that less than 100% efficient transmission of light waves. So that's, as a physicalist, that's what I'm more comfortable with. I'm comfortable with saying that the Big Bang is just wrong.
Well, that's a pretty good way of viewing it. Mainstream, of course, has adopted the Big Bang as a thesis, and so that presents this problem of where did the universe originate from.
I mean, to me, it's kind of a basic logic problem.
I think Hans is trying to address that. That's my understanding of what he's saying.
Well, Hans, you had something to do with pulses. Based on what I was reading in your paper, it seems to me that the creation of mass does depend on these pulses, which would be a form of energy. So is that really an energy to matter thing? I see you muted, Hans. Let me unmute you. There you go. I unmuted you.
Can you still hear me?
I can hear you now.
That's good.
You were muted for a while.
Good. In the beginning of time, none of these stochastic processes has done anything. So the function, the balloon of the universe was completely flat.
What about flatness?
The balloon was flat, was not filled.
Yes.
And these processes started to run over the full parameter space. It's not a single point, it was a full parameter space. So it's a flat space where nothing is in it. Hello?
It's just that seems to be, I'm not sure I can relate that to anything you've said previously. Flat space?
It has no volume.
The volume is zero. And
volume is zero.
A field can be described by a function. The target space of a function, a multidimensional function. And if that function equals its parameter space, then it is flat.
And the flatness helps us explain what? It's just I'm not sure how this relates to anything that we were talking about. We were talking about, philosophically about, can something come out of nothing, and whether you were saying that.
In the model, it's not coming out of nothing. In the model, you have a vector space, and on this vector space are living a series of separable helper spaces and a single non-separable helper space. And what's happening is that these separable helper spaces, where everything is discrete, are embedded into the non-separable helper space, where most of the things are continuous. So there is content moved from one part of the model to another part of the model. It has no name. For me, it is something that had no volume and is becoming volume in the continuum. It had a discrete value, and it was it breaks the symmetry of the non-separable helper space, and that's why it triggers a volume. And the mathematicians call that the Green's function of the field, and the little bit of volume that is added is exactly the volume of the Green's function of the field.
That's good. I like this whole idea. Here's my question, Hans. Have you talked about this with any cosmologists or anybody who, has an interest in cosmology, and what is their reaction, if any?
I speak with some cosmologists, and they only applaud what I'm doing. You understand applaud? They say I'm busy very well. And once I was very sick, and I said I was going to stop my reporting on my project, and they asked me very hard to go on with it. So they find it good. But I also asked to improve on my model, and they said, and I promised a bottle of fine cognac if they could improve on my model, or if they could disprove my model. And there's a claim on the my website for this fact, and they said you have to drink it yourself. We can hardly do it better.
Well, I'm sort of wondering if anybody really understands what you're talking about. Do they understand what you're talking about, do you think?
Yes, what I use is simple mathematics. As soon as you do things like how do you call it? Differential geometry and things like that. You run into the Green's functions and all those things. That's what the kind of mathematics that I use. I use quaternionic differential calculus, which is very close to. I developed it myself with quaternionic number theory, but in fact they are the Maxwell equations to a certain degree. Maxwell equations are derived from observations. I derive them from number systems and number theory and algebras. They are common mathematics. There's nothing difficult to it. I may be the first that constructed a complete quaternionic differential calculus with partial differential equations, and I use that a lot. And there are not so many people that do that. I think maybe I'm the only one.
I think you are. I guess what my reaction is that I think it's pretty interesting approach. I'm just kind of surprised that no academics. I guess the people that you're talking to, are these academics with that are in universities or what?
I sent my pointers to my theories and my papers to anyone that I know of. Leonard Susskind, Gerard het Hoofd, everybody who does something, and especially the scholars never react on such things. So, and I have no.
Basically, you're dealing with people who think they're much smarter than everybody else, and anybody who would be sending papers to them isn't very smart.
Yeah, they must be able to understand all these things. But I'm have done my career in high-tech industry and lost connection with universities. And I started this whole project when I was 6 to 8. So I lost most of my connections. People died, or at least I had long time had no connection with anybody in the academic world. And I asked some professors to support me, for example, to publish on RXIV. You need their support and registration and support from someone, and they didn't dare to give me support because what I write is very provocative.
I'm not sure why it's provocative. Why do you think so?
Well, I come to conclusions that are quite different and far off from what contemporary physics is teaching their students. For example, I derive what the electric charges are, and from symmetry rules, I have my own theory of gravitation, and can do a lot with that. And I understand. I think most of the basics of physics, and I can derive it from its fundaments that were discovered 80 years ago by von Neumann and Birkhoff. And there have been some people that work with this quantum logic stuff, and also some mathematicians did so, but they are not quite popular with physicists. that do particle physics also, they are mostly experimentalists, and they don't like to use the axiomatic approach. What I do is an axiomatic approach.
So now we're back to Bill Lucas's criticism of modern physics. It doesn't employ logic.
Yeah, it's too bad we don't have Bill here. So does anyone have any further questions for about this paper here? And did we just lose Hans? I don't see him listed on the list of participants here. You still there, Hans?
Could be. He probably
okay.
called it up.
Okay, well, we may have to wait for him to go on. So, okay, so that was an interesting discussion of Hans's ideas about that. So he presented his paper that was in the link there. So generating mass from nothing. I'm going to make a note of that in my notes here for today. So we just talked about it. Okay, so let's get on to another topic then.
So I have a topic to discuss. If you're, oh, I got a phone call. Sorry.
Okay, well, Harry's going to go there. So if no one else has any other topics they'd like to discuss, I'm just going to go down the list of information on atomic theory that we have. So I think the next one I had on my list here is ionization energy. So this is going down a list that I got from Bill Lucas of things that any atomic theory is going to need to explain. And so one of these things is called the ionization energy. And this is just the amount of energy it takes to eject an electron from an atom. And so if you have, let's see, oh, Hans is back here. But
yeah, sorry.
We got some noise.
I was thrown out of the system, sorry.
Okay. Glad to see you back. So, but we're moving on to a different topic.
No, that's good to me.
So we are going to be talking about atomic ionization energy. And so if you have an atom that has 4 electrons around it, that would be beryllium. It takes a certain amount of energy to kick the first electron out of there. Now, if you keep on giving it more energy, you can kick the second electron out of there and keep it out. And more energy, you can kick the third one out. And finally, you can kick all 4 electrons out of an atom, which is kind of a remarkable property that an atom can still stay together even though you completely removed all of the opposing negative charges, right? So, and it becomes totally positively charged. But these things just don't come off with, you know, the same amount of energy. So if you have like 4 electrons that have to come off, it doesn't take the same increase in energy to kick those electrons off. There's a specific pattern that shows up. So I'm going to share a chart here for the ionization energies for the argon atom. Argon's a pretty big atom. It's got 18 electrons on it. So I'm going to share with you the chart on that. Let's see here. Where is that? Okay, let's see here. Okay. So ignore the stuff on the text here. All I want you to look at here is this chart that comes from Web Elements, which shows the first 18 ionization anaphthalate, however you pronounce that, of argon. So on, let's see, where's my pointer here? Do I still have access to a pointer? Well, in any case, so on the very right-hand side, there is the list of the ionization energies from the first electron to the 18th electron. And so like it takes 1520 amounts of energy to ionize off that second one. In order to, the first one to ionize off the second one takes 2665. But then to ionize off the third one is 3931. And on the chart to the left of it, that's just showing the relative energy that it's taking to ionize these things off. So you can see for the first 8 electrons, the amount of energy it takes to do the ionization is a relatively similar increment. But then when you get to the 9th electron, you see there's a jump. So it's not a smooth increase to get the 9th one somehow takes a lot more energy to pull off. But then for the next 8 electrons, it takes more or less a linear increase. But then when we get to the last 2 electrons, there's a humongous jump in the amount of energy it takes to pull those last 2 electrons out of the atom. So we can see we have this pattern here. We have this pattern of 8, 8, and 2. And if you get into some of the larger atoms, you'll see this same kind of pattern repeating. Like 8, 8, there's some 6s, there's some 2s. And this is actually a fairly large motivator for the idea that atoms have shells. So for example, this is suggesting that there's a shell of 8 electrons, and then another shell of 8 electrons, and then another shell of 2. So let's just go and look at how this looks like in, for example, like a shell model here. So I'm going to share my screen. We're going to go to the website. This is called Web Elements here. And this has a description of all of the known properties of all the known atoms. So now let's go and we were looking at argon, so let's go look at argon. So argon has 18, has an atomic weight of 18. Means it has 18 protons and 18 electrons. And if we look at the pretty picture for argon, so this is kind of the picture they have where you've got the 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Around the outer shell, you've got 8 around the inner shell, and then you've got 2 in the middle. So I think this is generally where they get this idea of shells. It basically comes from the ionization data here. And that's something you can see pretty directly from just looking at the ionization chart as you plot this thing. So that's interesting. So any atomic theory that you come up with has got to explain why that happens. And so mainstream kind of explains that with these shells. Let's see here. Now there's other things you can look at here. Effective nuclear charges, electron binding energies. I think there was an interactive thing here. So we have the shell structure, which is 2.8.8. Let's see here. I thought they had an interactive electron shell thing here. But that's basically an explanation of the ionization energy. Did anybody have any questions about that, or have any suggestions as to why atoms exhibit this?
Yeah, I have kind of a question. Doesn't it also depend on more on the wavelength or frequency too? Maybe I'm or maybe I'm mistaken something else. But I always thought it was more dependent on the wavelength of the energy of kicking those electrons out.
Well, maybe you're confusing that with the spectra, because I think people may confuse this as that there's this idea that when an electron transitions from one state to another, it produces a particular frequency. But that is not what we're talking about here. All we're talking about here is that you're trying to figure out how much energy, I don't know, in the form of, because typically you would ionize things by putting them in a gas and then running an electrical charge through them. And somehow you can tell when you've ionized off an electron. I'm not quite sure how they do it, but it doesn't have anything to do with the spectra. The spectra is the different frequencies of light that you get out while you're doing this ionization. But the ionization energy is just the amount of energy it takes to kick an electron permanently out of an atom. Does that make that clearer?
Yeah, it does. But I was still thinking that I thought Einstein even actually won a prize on this. Is that maybe I'm not ionization maybe is a little bit different than what I'm thinking of, but like when you shine light on something and the electrons come off of it, there's a certain, once you get to a certain frequency, you'll notice that more electrons come off of it, but it has nothing to do with the energy or the volume of the frequency. It has more to do with the frequency itself.
Yeah, that's the photoelectric effect.
That's what I'm thinking. Thanks.
And that is a form of ionization, but they weren't attempting to ionize every single electron from the surface of the atom. See, this experiment is ionization, but they're trying to actually remove all the electrons from an atom.
Okay, well that brings up another question. Why would the frequency play a big part in ejecting some electrons, but not have a part in ejecting all the electrons?
Well, I think that would just be a matter of the amount of energy involved here. Like I said, I'm not quite sure how they do these experiments, but I can see that it is confusing that the photoelectric experiment is really a different kind of thing. They're using different frequencies, and they're showing that if the frequency is below a certain threshold, that it just doesn't have enough energy to eject any electrons, no matter how bright it is. You know, it's like, that was the thing that they couldn't explain, which is that if all energy is equal, then if I have a lower frequency energy at 600 nanometers or something like that, and I can shine every single light in the world at 600 nanometers, and I won't get any ionizations. But if I have something that has shorter wavelength, like 300 nanometers, that is capable of doing the kicking electrons out of the surface. So it really didn't matter the energy. But like I said, that is a different experiment here. This would be an experiment where you just throw the light of a very, very, very shortest or most powerful ionizing thing that you can think of, and you keep on hitting it until you knock all the electrons out of a particular atom. And if you do that, you would get a chart like I'm showing here, showing that the first 8 electrons come out at relatively linear rate, and then there's a jump in the amount of required power. You could think of, like, I don't know, if you're doing this like a photoelectric, like the number of light bulbs you have pointing down at the thing, and but the next 8 take more, and then finally the last 2 are really stubborn, and you have to really apply which is this kJ, this is kilojoules per mole, 40,000 kilojoules per mole to finally eject those last two.
Okay, well, thanks. That does clear that up. I guess just to throw that out there, one explanation I would immediately think of is that the last two are closer to the orbit, closer to the nucleus, although I guess they don't like, or the shell, I guess, is closer to the nucleus. Therefore, they're more tightly bound.
Yeah, that could be going back to like kind of like this shell structure of argon. Although I don't think people really, even mainstream, believe that this is true. if you were to look at the shell structure, they have what like S and P's, and these things look like kind of balloon animals twisted together, kind of thing, and it's really hard to see what that. I mean, they used to have pictures of that in here, so I'm kind of disappointed that they've actually reduced the amount of information that they have on this website to show what's going on here. Now, if Bill Lucas is here, he would remind you that it's impossible for these electrons to actually be orbiting like this around the nucleus, because otherwise they would be radiating energy. And so this kind of picture is not really possible. And so mainstream will go and say, well, they're not really orbiting, they're in a probabilistic cloud, and because they're in a probabilistic cloud, that means they're not actually moving. Yeah, right. That seems like a lot of ad hoc hand waving. But I believe Bill Lucas is, he solves this problem by basically saying that the electrons are in static arrangement. So this particular picture might be okay, but it would mean that those electrons are actually stuck in place, and I'm not actually moving. So there's nothing wrong with this picture as long as the electrons aren't moving, right? So Bill Lucas's model is somewhat like, I mean, it's not like exactly like this, but he's got static arrangements for electrons. Now, I of course have my own ideas about this. I am one of my specialties is atomic physics, and the problem I have with that picture is that how can these electrons stay in their shells just kind of suspended, as if they were all connected or something like that? I mean, there's nothing wrong with them being static, but there's got to be some reason why they just don't all collapse into the middle, because these things are all being attracted to the proton, right? And by our knowledge of Coulomb's law, all these things should just simply collapse straight into the nucleus, right? There's nothing holding them up, right? And I think that Lucas's model would argue that it's the repulsion of the electrons themselves which keeps them in their respective locations. So, one of these electrons might be repelling the other one such that, but this is a very careful balance it would have to be making. I mean, this is like a seal balancing a ball on its nose. Maybe I've heard it's like 3 balls being balanced on his nose, because there's still nothing physically preventing any jostling, prevent this thing from just flying apart if it's got all these electrons in the air. And so that's where I would have my problem with any kind of model like that. And so I have a way to solve this problem. And the way I saw...
May I make a remark?
Go ahead.
In the paper that I referred at the beginning, this 3-page paper, there is a paragraph called modules, and that says that the stochastic process of the module, so not of the components of the module, but also the module itself, so the atom itself has a stochastic process, and that stochastic process has a characteristic function. And the characteristic function of this composed module equals the superposition of the characteristic functions of the stochastic functions of the components. So the electrons that are being part of the atom are giving places by these superposition coefficients. Now these superposition coefficients are solutions of the Helmholtz equation. And the Helmholtz equation gives exactly these oscillations that give these shells that you were talking about in the beginning. They are spherical solutions of the Helmholtz equations, and you can find places in Wikipedia that I have shown in the chat box. If you go there in Wikipedia for the Helmholtz equation, then and you look at the three-dimensional solutions, you see these kinds of solutions. And if you look at the spherical harmonics of these, then you see that these typical solutions that you often see when drawings are made of simple atoms.
Okay, well that sounds more like the mainstream kind of explanation for that.
Yeah, but in the Hilbert-Book model uses stochastic processes, and these stochastic processes are generating the electrons and the elementary particles, but they are also stochastic processes at a higher level that generate the composed modules, which are, for example, the atoms. And these stochastic processes, they take care that these electrons are behaving as they are doing and move around, also oscillate according to these different oscillation figures.
Okay, so Mitch sent us around let's see, this is the orbital kind of thing. So you can kind of see what these things theoretically look like. So it's like, that's argon.
But I don't really understand what your point is about this whole thing.
We're explaining, we're just looking at data here. So so the mainstream explanation of what these orbitals look like, you know, like these balloon animal things, some of them don't look so bad, but some of these others, like there's a donut.
Well, Hans just explained where all this comes from. I mean, he just explained the theory of it.
Well, that's one possible thing.
Do you disagree with that theory, or what? What's the point?
Well, I certainly disagree with it. So
why?
Because it still doesn't give you the physical idea of why. I mean, he's just saying that according to mathematical equations, you can arrange things in shells, which is basically the same thing that mainstream is doing with their wave equations, which I disagree with.
Let me with wave equations.
Yeah, I mean, you can see the kind of shapes that the mainstream is suggesting that these things have, and I think that's just completely preposterous.
Why? I don't understand. They are mathematical solutions, and if you put them in a computer and draw these oscillations, you get exactly these figures.
Yeah, and I think that's completely preposterous.
Why?
I mean, this doesn't really motivate you to think, you know, why is it that we have actually two sets? There should be two sets of 8 in here. I only see two things in here.
You make the mistake that the electron is some kind of ball or something concrete that's oscillating around. What is oscillating is the target centrum of where the electron is going to be generated. That is oscillating, not the electron itself. Also, its charges, they stay at the center of the atom. The charges are not oscillating. No, the places where you can detect the electron the target of that stochastic function that use that as a target, that is oscillating. The stochastic process of the electron is multiplied by a superposition coefficient, and this superposition coefficient is a solution of the Helmholtz equation. That solution makes these oscillations, and so what is oscillating is the target where these stochastic processes trying to generate the electron.
Yes, but none of that, I mean, I'm not saying that any of that doesn't have a lot of justification behind it. I'm just saying, it's purely mathematics, but as a physicalist, I have a lot of problems with that.
What is a physicalist?
A physicalist says that he takes things he sees in the world, physical things, you know, like, I don't know, like Lego bricks or whatnot.
That you ever see an electron.
Squares.
That you ever see an electron.
Well, we see them in use in CRTs, so I'm pretty sure that they are individual
CRTs.
Well, in any case, the thing is that the one reason why I don't like any of these solutions as a physicalist is because I have alternate solutions that don't require to use any math.
Your solutions don't work.
No, my solutions
these are much closer. These solutions that I'm talking about are much closer than what people see in doing their very sophisticated experiments. They are not playing with Lego blocks or so. They are doing real experiments in their laboratories and come to conclusions that are close to 10-digit accurate values.
Yes, but it doesn't make any logical sense. You have to suspend the logic in order
mathematics makes logical sense.
Well, the thing is that I had already motivated the problems with any time you have electrons outside of a proton field. I mean, Earnshaw's law says that there is no stable configuration that those electrons can take. Even if the mathematics say that there can be, Earnshaw's law would immediately discredit that and say that that's not possible. Once again, the role of logic here.
So
the role of logic here, I mean, you have to suspend basically Earnshaw's law to accept any of that.
Franklin, this is due to the fact that you don't understand mathematics very well.
No, I understand mathematics, and I understand that they don't provide the physical basis for a lot of things.
They do.
They don't. But that is a matter of opinion, really. I mean, mathematic people will do that, but as an opposing viewpoint,
theoretical physics do this as well. They only use mathematics to do their theory building, the model building.
Yes, and I believe that we started that, and that is actually one of the big problems in physics in the last 100 years is this discarding of the physical. See,
they achieved a lot of.
They have completely abandoned simple ideas like an electron is like a particle, you know, just as much as this square block is a particle.
It can still be a particle.
They have completely abandoned that idea.
No, they refined the idea.
Tell you what. See, now the reason why I believe all of that is false is because it can be explained more easily in physical terms. So I'm gonna just give you what my opinion is on how this ionization energy information can be explained, because you need to explain fundamentally this chart. So why is it
the point of why this came up in the discussion, so you can give your theory.
Yeah, I mean, I gave a chance for everyone to give their theory. Hans has given his theory. I've tried to give the motivations behind the mainstream theory, and I've given motivations behind why there's problems with the mainstream theory. You know, basically they can't be orbiting. And if they're not orbiting, then how do they stay in their shells, right? That's the problem, right? So there's a problem with mainstream theory. There's a problem with Lucas theory. So I have a suggestion that solves that last problem, which is how is it they can stay in their shells, all right? And the way that I solve that is that I have to get rid of one of the fundamental tenets of atomic theory, which is that all the protons are locked into the middle in the nucleus. That was by the Rutherford experiment done 100 years ago.
Evidence.
Hmm?
You're saying experimental factual evidence is wrong.
No, I'm saying that the interpretation is wrong. The interpretation that Rutherford made, which was that he stuck all the positive charges into the nucleus, just because, I mean, what was the experimental evidence that Rutherford had? I mean, so this is the Rutherford experiment here. On your left-hand side here, this is the only result that you see, is that depending on the scattering angle, you're
denying a fundamental experiment. Okay, what else? Where do we go from there?
Okay, so if we fundamentally deny Rutherford's assertion that all the positive charges are in the nucleus, then we can go back to more like the original discarded thing, which is that an atom is made out of just mixed positive and negative charges. So this was kind of referred to as like the plum pudding model, right? So if you have an electron and you have a proton, that they would just go together, and that if you had a couple more protons and electrons, that they would just link up. So I have like this checkerboard thing here. So the thing is that the protons are not in the middle with two electrons going around. So this is the conventional. You have two protons which can't possibly stick together with two electrons flying around the outside. This is the conventional.
All right, that's fine. All right, so based on your model, how do you explain the experimental results?
So based on the experimental results, so if you disregard that and just think that the electrons are bound with protons, then the experimental result says, how much energy does it take to pull the electron off, right? So you get that much energy. So that is the first ionization energy. That is the first ionization energy. And then you would think that it would take an amount of energy to pull off the second electron. So, but that's relatively easy to prove with just two of them. So,
yeah, but you didn't answer my question. How do you explain the Rutherford results with your model?
I explain the Rutherford results with my model as being due to the fact that when you have the incoming, really the only thing I have to explain is why is it we get these high angle reflections out of the data. Now in my models, a full atom looks like this, right? Now the thing is that it's very thin across most areas. Most time, if you shoot a particle like a bullet through this, you only have to go through like one layer of atom to get through it. So it's very, very thin. The only place where it's very thick is if you hit it straight on its axes. If you hit it on one of its axes, then it's very thick. And I did calculations that reproduce basically the Rutherford results by calculating if you just randomly oriented this and you shot things at it, what reflection rate would you expect during the times that, if it can't go through the main axis and has to reflect, then you would get a chart that looks just like the Rutherford, predicting a small percentage of high angle reflections. But for the vast majority of the orientations, it goes straight through. So I can explain the Rutherford data with this model using statistical analysis. So there's more than one way you can interpret that. Plus the data that Rutherford actually came up with was actually pretty bad. So that's the point of this chart that I have here on the left with the blue bars. And this is the error in the data from the original Rutherford chart. Now it looks very nice in this chart here, but this is charted exponentially. And an exponential chart hides a host of evils. And you can see that this is the error bar. So like on the 22.5 degree measurement, it's off by nearly 27% off prediction. Same thing for 15. It's off by 25%. I mean, being off by 25% from your prediction is usually pretty bad, right? And same thing down here. I mean, this is not really even close.
Was done in 1901 or whatever. When was it done?
It's like 1901 about.
So, you know, I'll let that pass.
But I'm just saying that at the time with this data, I mean, they shouldn't have said this was a match. I mean, this is really poor matching. It only looks good only if you plot it on an exponential scale where all these
in your opinion,
differences get hidden. No, I mean, this is not an opinion. This chart is charted directly off of the data that was found in the paper, and you can compare it directly against the predicted values.
Based
and
on
this
an
is the error that you get.
1901 with crude equipment.
That's right. So it's very crude, but even with modern equipment,
don't you think that they've tested this? You know, that the current physics is done. You know, that they aren't basing their thinking on crude experiments done in 1901. That they would have found something amiss and would have corrected this mistake by now if it was wrong?
Actually not, surprisingly, because that was one definite area of interest I said, okay, so this is a crude experiment, so we got much better equipment now, right? So show me a modern replication of the Rutherford experiment. Now, the closest thing I could come up with are people in junior physics labs and universities replicating this. But even they find out they can only replicate the Rutherford formula within a very narrow angle range. That outside of that, it really doesn't do that. And then they wave their hands saying, well, that's because we have a finite width of our detector, even though they have much better equipment than Rutherford ever had available to him. And they just brush it off.
I don't know what your point is. What's your point?
The point is that this experiment, this got people to believe that the nucleus was tiny, but this data, it by itself shouldn't have been enough to do that. But yet people continue to believe
nuclear reactors, they do nuclear reactions, and they have cross sections. Okay, and so presumably these cross sections and the studies that are all based on this Rutherford assumption about the nucleus being tiny, and they've created atomic bombs and done all this stuff. So presumably their conclusions are pretty correct, I would think.
Well, I think not a lot actually relies on the nucleus being
I'm not really
tiny.
buying this argument, Franklin, that you're smarter than the whole physics community that's been working on this for over 100 years. I mean, I'm
basically
really kind of skeptical. And aside from the fact that you know nothing about physics, zero essentially, doesn't really help your case any.
No, I mean, that would be the remarkable case. If I was at all right,
if somebody who knew nothing about physics would turn out to be right on a subject like this, that would really be remarkable.
Yes, it would be remarkable. But that's why people like me work on stuff like this.
Well, I think your imagination has inflated your ego way beyond its actual capabilities.
Yes, as I say, I am a legend in my own mind.
Yeah, right.
Exactly. But yes, in fact, if this were true, then it would be a complete embarrassment to the physics community to go back and say, oh, yeah, Rutherford really didn't prove that, did he?
Even the modern replications don't physics, I would think that would really be an embarrassment, yes. But
in any case,
I'm not really sure
what this means.
What's the point of all this? I mean, I don't really see what any of this means. You're just saying that you have a model. You think that what Rutherford said was wrong, and you have a model that you think is better based upon your not understanding anything about mathematics and not understanding anything about physics, somehow that makes you right.
Oh, but I do understand a great deal about physics. This is why I write papers. This is why I have the formulas here of what we know. I know what,
we
I
just
know
had a
Coulomb's
discussion,
law.
and you said, in effect, basically, that everything that Hans said was wrong, in so many words, and yet you don't understand anything about what the reasoning was, the mathematics behind it, or any of the physical experiments that confirm, that particular model that Hans has. You know nothing about those things, and yet you've decided that he's wrong.
No, I know about the physical experiments. This chart here of the first 18 ionizations of argon, we know that. We totally know that.
You're just making
so
up
the only
stuff.
thing is
Well,
that
this is what
that
you usually do,
need
frankly, is you just make up stuff. So tell me, what is your model of the atom and why you think your model is right?
Okay, so let's just get down to the brass tacks here. Okay, so I say, and most people would not agree with me, that the atom looks like this. So if you can see my video here, you can see it's an octahedral buildup of bricks here. Okay, now I think this might be an argon atom, but in order to explain this, what we see here in the chart, you can see that if you were to try to take pieces off of this atom, that they would be at about the same energy level because they're basically in the same place. So clearly, like if you were to remove ionize the atoms off the tips here, what I have shown in red, that would take about the same amount of energy. And in this case,
well, what's holding this thing together? In your case, what you have is a force of friction that you basically have these physical, there's a lot of complexity in this model. You just took some Lego blocks and stuck it together. Okay, that's not what an atom isn't Lego blocks. So what's
actually probably closer than you think.
What's holding it together in this particular configuration that you've imagined?
That would be just purely the electrostatic force. So this is a magnified view of the core of that atom.
But we've already established you know nothing about the electrostatic force or the electromagnetism.
No, I know everything.
I know. So you know what you're talking about because you're so smart. But
yes, I am so smart.
Basic knowledge of electromagnetic theory.
We know, the only electromagnetic theory you need to know here is that positive charge attracts negative charge. I think we know that. That's Coulomb's law. So all you have holding this atom together is nothing but the Coulomb's law. And as Bill Lucas has pointed out, experimentally, the only force that we find inside the atom is the electrostatic force. So that's another thing that you have to explain.
Electrons are shaped like children's building blocks?
Yes, electrons and protons are shaped like children's building blocks and can be considered as blocks for purposes of constructing atoms. So, but all it takes is a very simple concept is that you've got a positive, you've got a negative charge, you put them together. Now, a neutron is also a positive and negative charge. I've colored them in white, but they have the same properties. And these are Velcro blocks, which replicate the fact that you can only put negative against positive, because otherwise this thing would fall apart. So what's holding this together is just a series of opposite positive and negative charges. So it's going to be positive, negative, positive, negative, positive, negative, positive, negative, and they all match up. So this is what's actually holding the shells together in the electrons that we observed. There are shells, but they're supported by an infrastructure of neutrons and protons. So this is helium. So, but if you add another layer onto this, so you get lithium here. And I have to put it precisely on, otherwise it doesn't work. So you have that the electron off of lithium can be more easily extracted than the electrons which are stuck in as part of the helium, right? And then if you stuck another one here, then you'd get beryllium, and then you would see that it's the two outer electrons will ionize out at about the same energy.
Where are the neutrons in this thing? I don't.
The neutrons are the white things in my model here.
Well, what holds them together?
Once again, they are made out of a positive and a negative.
So what holds them together?
They are made out of a positive and negative charge. In my model, the neutrons really are just a positron electron dipole. So everything is held together by just simple electrostatic charge, and it's held in place by the concept that these are space-filling particles and that they do have effectively a surface through which the other particles cannot penetrate. So other models have to try and come up with like a short-range repulsive force so that these things just don't immediately collapse into nothing. But I say, I use the more common sense idea that if we can think of the positron or protons and electrons as having physical surfaces, that those physical surfaces are what keeps them apart, not any kind of repulsive force. But I'm just saying the key solution that I'm coming up here with is that I can keep the electrons in the static arrangement, so they don't have to fly around. And I'm justifying that by saying there is a supporting infrastructure of protons and neutrons to hold this thing up, so that when you start piling up on top of each other, you get a shape like this. And the shape that I have here is not arbitrary. This is built up mostly on that ionization data, where I figured out where I would put each one of these blocks has to match up with the observed ionization data. And you can build this model like any which way you want, and most of them will not work. So that's why I came up with this. And basically, it builds out shell-wise. I mean, I have my picture here. So this is a picture of like an atom, and you can see there's different colors. So each one of those different colors actually represents one row in the periodic table. So like in the very center, there's a dark blue, but as you build out, there's a darker blue, and you get oranges, reds, greens, and oranges. That corresponds to each level in the periodic table. And this is why we have, I mean, if you look in the periodic table, there's a lot of symmetry around the number, say, 4. And that's because you have to, there's actually these 4 vertices on the outside. So you build on the outside in groups of 4, basically, until you get to the ends of the periodic table, in which case you're building up on top and on the bottom.
Okay, well, we're running out of time. I would like you to tell me whether light is a particle or a wave.
It's a wave.
And
pure
how
wave.
do you know that?
How do I know that? Well, as a physicalist, I know that we do have things called waves.
I don't know how a physicalist can say that light is a wave, but anyway.
Well, we know we have a physicalist, we know that sound is a wave.
To me, sounds like a contradiction. Because
sound is a wave. I mean, if you're trying to determine whether light is a wave or a particle, we have to look, as a physicalist, look at things that we can see physically. Now, if light were like a particle, then it would be like a bullet versus a wave, like a sound wave or a wave through water.
Okay, so as a physicalist,
closest to?
As a physicalist, it makes more sense to me that light would be a bullet than a wave. So
well, then you'd have to explain.
That's what I don't follow about your whole philosophy and the word physicalist, which you claim to.
Then you would have to explain the fact that you would have to explain the very interesting experiment that the velocity of light does not depend upon the speed of its emitter. Now,
well,
that can be easily explained.
To do with physicalist. Basically, you're telling me that light, as a physicalist who's telling me that atoms are composed of Lego blocks because you're a physicalist. Now you're telling me that light is a wave, which is something that's not physical that I can see. And, you know, it seems to me that's like a contradiction of your whole
Well, as a physicalist, if I'm saying that light is a wave, I have to provide a physical medium for it to go through.
No, you don't. Why do you need that?
As a physicalist, everything has to be physical. So if I'm saying there's a wave, then there must be a medium. The medium must be something like air, like water.
What is this Coulomb field that you've been talking about that holds your atoms together if it's not physical?
It's totally physical. Everything in my model.
It's just an invention. It's a hypothetical thing that allows you to stick Lego blocks together. So it doesn't look to me like it exists.
No, physically, the attraction is based on the interaction of waves that come off these particles in opposite phases, which physically has been shown to happen. You can create attractive forces between pulsing balloons, which are pulsing out of phase in water. So as a physicalist, I can see, aha, that is a process which can actually happen and has been experimentally demonstrated. And that is the process which causes opposite charges to be basically pushed to each other.
So you sort of got yourself into this contradiction where you're saying that, you can infer that something exists and so therefore it's a physical reality. But in the case of the atom, you've decided that you can infer that that these forces exist or these things exist. And so you've decided that they're made up of Lego blocks. I don't see the logic in any of that.
Well, I would say that logic in thinking that they're Lego blocks is because these Lego blocks are, in fact, made out of atoms, right? Fundamentally, no one would deny that, right?
Okay, I guess we've run out of time.
The properties
trying to make logic out of illogic.
No, it's all perfectly logical. The thing is that we can observe the properties of physical particles. Now, my only claim is that if you take this block and you break it up into the tiniest pieces, that you're still going to get something that behaves like a block, meaning I can still squeeze it between my fingers. It still puts up resistance. It takes up a finite amount of space. And if I have another particle of the same size, they cannot pass through each other. And they will do exactly the same thing as I can observe them to do macroscopically. Now, to me, that is a perfectly reasonable conclusion to say that the microscopic works exactly the same as the macroscopic. And that's the only bit of logic that I'm using here to say that whether this particle is the size of an alphabet block or whether I shrink it down to the size of an actual electron, they can still do this. They can still form geometrical structures exactly like this, by analogy. And I don't think that that is a very far stretch. And of course, for a physicalist, the appeal of this is that it doesn't require any math. I mean, just looking at this, you can tell what beryllium is going to do. You can tell its symmetry. You can tell how many pieces it's got. You can tell where the neutrons are. And you can see why the ionizations would be why it is. Without any math, you can just visually see that. So that is the appeal for a physical model. I
recommend that you go to the physics laboratories and tell the physicists that you've made this amazing discovery and see how they.
Well, they all, of course, think I'm crazy because they.
Well, I think you're crazy too.
They would have that. They would bring me back to Rutherford, and I would show them. Well, Rutherford sucks.
You're going to tell people that atoms are made out of Lego blocks.
Exactly.
That's sort of illogical, but anyway.
Actually, someone actually wrote a book on that. The physics of. It wasn't my Lego. Just a minute. Just hold on a second because I want to show you this book. Just a second. I think you'll get a kick out of it, and this will end our theory. So this book is called Particle Physics Brick by Brick, and this is a very nice book that someone has put together, explaining particle physics using Lego bricks, and they're doing things like explaining quarks and atoms and.
So it's already been done.
Well, I'm just saying that it may not be as ridiculous as you think because someone did it. Now, this may not be the correct. I'm going to have to write this guy and say, you're really close, except that it should really look more like this. See,
Yeah,
his
right.
atoms are very long constructions that look like this. You see, he's got these big stacks. That's what his atoms look like. But that really does not explain how the ionization energies would come off with such a long stack, because there's no grouping.
Well, I think I know how the ionization energies depend on what kind of glue you use to stick the blocks together.
But there is no glue used in Lego bricks, right? Okay. Well, in any case, but we were just looking at just this whole ionization thing and how various models can explain that data. So we looked at, like I said, we looked at mainstream. We looked at Hans's explanation, mathematical explanation. We looked at Bill Lucas's explanation, and we looked at my explanation. So people can pick amongst what makes more sense to them. But I believe that will do it for today's episode of the Science Chat. And I did want to once again encourage people to come to the conference. I believe there was an announcement saying that if you wish to stay at the conference center, you can stay for $69 a night, but you will need to share with 3 other people. There's 3 people per room, and I'm not sure how they are arranging who stays with who. Maybe you just get randomly stuck with me or something like that. I don't know. But the conference is coming up. I'm thinking about going myself, but right now we don't have a lot of people going to the conference. But I have been to like the last conference we had in Vancouver, which was relatively small. But even that, I think that can be more interesting, because we had opportunity to do things like we could take the entire crowd to go visit one of our members' home and just hang out for a while and discuss things casually. That's things that you can't do if you've got hundreds and hundreds of people coming to your conference. So there's more of an opportunity to discuss things in a small group setting in a small conference versus a really huge conference. But that is what's going on. So thank you for everyone's participation. Thank you, Hans, for presenting your new paper on how matter comes from nothing. Be something interesting to think about. We can agree or disagree, or we can agree to disagree. But that's what we're here for at the Natural Philosophy Society, to discuss all things in the tiny hope that one of us will be right. And as Harry says, I will have to have, if anything that I say is correct, it's going to be a complete embarrassment to the last 100 years of physics, right? But that's what makes it exciting, right? It's like I could be like someone comes out of nowhere and suddenly discovers some major thing wrong with physics, right? And the way physics are going, I think a lot of us dissident scientists think that physics ran off the rails long ago, usually around the time Einstein showed up, and that there are better ways to explain things. So, but if you guys got any of those better explanations, let me know. And this Science Chat is here for you to present your ideas and discuss them. All right, so I believe that will do it for this week's episode. And next week we have a special guest, Ian Cohen, will be presenting his paper about electromagnetic waves compared to regular waves. So that may be very relevant to like that little discussion about, you know, whether light is a particle or a wave. So don't miss that. So we'll definitely be doing that next week. And that will do it for this week.